Our next example is y equals 2 times the cube root of x minus 1 minus 1. And so our parent function for this example would be the cube root function. If you remember, this is also x to the 1/3 from a rational exponent unit. Our a value is 2, our h value is positive 1, and our k value is negative 1. And so those three things are going to perform the transformation. Step 3, knowing some points on the parent function. So I'm going to say, start with -8. I want 5 points for this one. So -8, -2, because the cube root of -8 is -2. -1, -1, 0, 0, 1, 1, and then 8, 2. And so knowing those points, we're going to perform the transformation to our new function. Our x values are going to shift to the right by 1. And our y values are going to get multiplied by 2, and then we're going to subtract 1 from it. All right, so I'm going to do these now verbally versus writing them down. So -8 plus 1 is -7. 2 times -2 minus 1 is -5. -1 plus 1 is 0. And then 2 times -1 is -2 minus 1 is -3. 0 plus 1 gives me 1. 2 times 0 minus 1 is -1. 1 plus 1 gives me 2. 2 times 1 is 2, minus 1 is 1. 8 plus 1 is 9. 2 times 2 minus 1 is 3. And so now I have 5 points to draw this. Remember, 0, 0 is our point of inflection. So our new point of inflection is transformed to 1, -1. We have the point 2, 1. Then we have the point 9, 3. We have the point 0, -3. And we have the point -7, -5. And so now we know the shape is going to look kind of like a elongated S, hit our point of inflection, curl back up, and go through that point there. Arrows on the ends because we know our domain for this is all real numbers as well as our range. And so there's our cubic function, y equals 2 times the cube root of x minus 1 minus 1. In this example, we're going to graph y equals 3 times 2 to the x minus 4. And so our parent function here is y equals 2 to the x. Now, our base can change. So this could be any number we want, but we're going to focus on 2. So that's our parent function. Our a value is 3. Our h value is 0. There is no plus or minus h in our exponent. And then our k value is -4. And so it's going to shift everything down for units. So 3 is we're going to take points from our parent function, xy. So at -1, our output is 1/2. At let's say 0, our output is 1 on the parent function. Right? So this is 2 to the x. At 1, we're at 2, and at 2, we're at 4. At 3, we're at 8. So we're going to transform this based on our rule for the transformation. Now our x values do not change because there is no h value, so I'm just going to copy those down, -1, 0, 1, 2, 3. Now my y values are going to be 3 times our y values minus 4. So at -1, we have 3 times 1/2 minus 4. So we would be at 2.5, -2.5. At 0, we're at 1 on the parent function, so 3 times 1 minus 4 is -1. At 1, we're at 2. 3 times 2 is 6, minus 4 is 2. 3 times 4 is 12. 12 minus 4 is 8. And then 3 times 8 is 24, minus 4 is 20. We can't fit that one on there, but if we could, we would have a point at 320. So to graph this, the first thing I'm going to do is I'm going to note that in our parent function, the asymptote was y equals 0. Well, we're going to shift that down 4 units. So I'm going to have an asymptote at y equals negative 4, which means our graph will never cross this line. So I want to draw that in. Now I'm going to plot my points. At negative 1, we're at negative 2.5. At 0, we're at negative 1. At 1, we're at 2. At 2, we're at 8. And at 3 would be at 20, so I can't fit that. So now I can graph my exponential function. I'm going to hug the asymptote and then slowly curve up. And now I'm going to exponentially go through these points. Okay, and so there we have the graph of y equals 3 times 2 to the x minus 4. Next example, we have a log function. It's base 2. And so our parent function would be log base 2 of x. And this has a vertical asymptote at x equals 0, so we know that's going to shift based on what happens in our a, h, and k values. So our a value is 1/2, our h value is negative 4, and our k value is positive 3. So 3, I know x equals 0 for our vertical asymptote is going to move to x equals negative 4. Right? It's going to shift whatever makes that 0 inside. So now, knowing some values on my original function, so at x equals 1/2, my y value is negative 1. At x equals 0, it's undefined. At x equals 1, my output is 0. When x equals 2, I'm at 1, and when x equals 4, I'm at 2. When I'm at 8, I would be at 3. And so now we can perform the transformation. All my x values are going to shift by subtracting 4 to them. And so 1/2 minus 4 is negative 3.5. 1 minus 4 is negative 3. 2 minus 4 is negative 2. 4 minus 4 is 0. 8 minus 4 is 4. And all my y values are going to change by 1/2 times my y values. And then I'm going to add 3 to it. So 1/2 of negative 1 is negative 1/2 plus 3 is positive 2.5. 1/2 of 0 is 0 plus 3 is 3. 1/2 of negative 2 is negative 1. Sorry, 1/2 of 1 is 1/2 plus 3 is 3.5. 1/2 of 2 is 1 plus 3 is 4. 1/2 of 3 is 3.5 plus 3 is 4.5. And so I'm going to start by graphing my vertical asymptote at x equals negative 4. And then my points are going to be negative 3.5, 2.5, negative 3, 3. Oop. Plotted the wrong point there. So negative 3.5, 2.5, negative 3, 3, negative 2, 3.5, 0, 4, 4, 4.5. And so our logarithmic function hugs our vertical asymptote. I'm going to draw this the best I can. And then it's going to start curling through those points. I didn't do a good job with that, but they should be going through these points here, going on its way. So that is the graph of a log function with a transformation. Our final function transformation is going to be our reciprocal function, and so that parent function of that is 1 over x. And so I would just want to make a note that there is a vertical asymptote at x equals 0 and a horizontal at y equals 0. So those are going to shift just like our x value shift and our y value shift. Okay, so step 2, our a value is 2, our h value is 3, and our k value is 4. So step 3 is we're going to make our little table. And really the big point that we had for 1 over x was when x is 1, y is positive 1. When x is negative 1, y was negative 1. You can plug in some other points, but those are the two we're going to use. I really care about the asymptotes on the transformation. So we know that we had x equals 0 for the vertical and y equals 0. So these are my asymptotes. I don't think I spelled it right there. So our transformation, right, is going to take all my x values and I'm going to add 3 to them. And all my y values, I'm going to multiply by 2. So 2 times y, and then I'm going to add 4 to them. So when I plug in a 1, I'm going to get a 4, and then 2 times 1 is 2 plus 4 is 6 is my new y value, and then negative 1, that's going to give me a negative, it's going to give me a 2, and 2 times negative 1 is negative 2 plus 4 is 2. And then my new asymptotes are going to be x equals 3, because I'm going to add 3 to this value, and my new y, my new horizontal asymptote is going to be y equals 4. And so I'm going to first draw those in our graph. I'm going to actually use a different color to kind of show where they go. So at x equals 3, I have my vertical asymptote. At y equals 4, I have my horizontal. And so with our reciprocal function, our graph's never going to cross those points or those lines. And so I'm going to plot the point 4, 6. That should be up. I'm going to plot the point 2, 2. And then to graph it, I know my graph hugs the asymptotes, curves through the points, and then we'll go back down towards the asymptotes. And we would have lines or arrows signifying that our function goes on forever in those directions. And so that's how you graph our reciprocal function.